All right, next up, let's take a look at the relationship between delta G, change in Gibbs free energy, and KEQ, the equilibrium constant. So it says the delta G for a reaction represents the increase or decrease in free energy for the complete conversion of reactants to products. However, this does not occur because reactions reach equilibrium where some of both are present. So we have a mathematical equation that shows a relationship between delta G and K. So let's take a look at that equation. We're going to go delta G naught. So we're going to just look at standard conditions. And so we end up with this. Delta G naught equals negative RT natural log of K. So change in free energy, of course, is delta G. That's in kilojoules per mole. Because that's in kilojoules, we need the ideal gas constant that has energy units in it. So 8.314 joules per mole Kelvin. Of course, T is our Kelvin temperature. And then K, again, this could be KEQ, so I just put K. KC for reactions with no gases, KP for reactions that have gases present in them. So we can actually calculate delta G with either KC or KP. So if it doesn't specify which one, use either one, that's fine. In fact, I've seen that in a number of situations. Sometimes it tells you use KC or you're given KC, so of course, whatever K you're given, just use that one. So qualitatively, what is the relationship between delta G and K? Let's start off with a spontaneous reaction, thermodynamically favored or products favored. So again, with a spontaneous reaction, that's a reaction that will occur all by itself. Delta G, of course, is negative. And if the products are favored, if you mix some chemicals together and they result in the formation of some other substances, you're going to end up with a KEQ that is relatively large. Now, if you go back to the equation, if K is big, if K is a number bigger than 1, and then you're going to end up with a delta G that is negative. So the natural log of a number greater than 1 is positive. And so because it's negative RT ln K, delta G is going to be negative. Conversely, if you have a non-spontaneous reaction, reactants favored, not thermodynamically favored, what does that mean? You take two chemicals, mix them together, and they do not result in the formation of products. Delta G is going to be positive, and K is small. So again, going back here, if K is small, if K is less than 1, then the natural log of that is going to be negative. So we have our double negative there. You end up with delta G being positive. So make sure it makes sense, both with the value magnitude of K and the sign of delta G and what is actually happening with those reactions. Now I know what some of you are thinking, what if K is 1? Well, then that means the natural log is 0, and so delta G equals 0. So don't worry about that. K is not going to be 1, and so we're going to end up with some positive or negative delta G value. If you take a look on page 689, figure 17.4 at the bottom of the page, it shows a relationship between Q, K, and delta G. And if Q, for example, is smaller than K, what that means about the spontaneity of the process and which way the reaction will proceed in order to reach equilibrium. And then also next to that, if Q is greater than K, what direction the equilibrium or reaction progresses in order to reach equilibrium. So take a look there and make sure you understand what is being presented in that figure. All right, so let's take a look on page 690, example 1717. It says, use the data in Appendix K, that's our table of thermodynamic data, to calculate Kp for the following reaction at 25 degrees Celsius. All right, so we need to use the delta GFs, And really the only one we care about is N2O because the delta GF of both N2 and O2 are 0. Remember, delta GFs for elements are 0. And so we get a delta G for the reaction of negative 208.4 kilojoules per mole, or negative 2.084 times 10 to the 5th joules per mole. So now we're going to use delta G to calculate K. So let's take a look in the book. It rearranges to isolate natural log of Kp. So we get delta G over negative RT, plug in our values, and we get 84.1. Take the inverse of natural log of both sides, and we end up with 3.3 times 10 to the 36. So of course, delta G being negative and pretty large negative value, negative 208, the magnitude is pretty high, is going to result in a K that is pretty big, and we see that 10 to the 36. All right, go ahead and do exercise number 83 on page 698. Be careful, it's not exactly like what you just did. All right, here's our setup, and there's a number of different ways you can do this. I decided to use concentrations and Kc, even though every substance in this reaction is a gas. That's still fine to do, you can do that. So I calculated initial concentrations for CO and Cl2, 0.600 each. And then it said that 3.3% of the chlorine had reacted. And so I took 3.3% of 0.6 and got the 0.0198 is how much the concentration decreased by, or how much the concentration of COCl2 increased by. And then I took those equilibrium concentrations, plugged them into the Kc expression, and calculated Kc, which then I use, oh here, let's put this here, which then I use to calculate delta G. Now, something that's interesting here, and in fact, I did this a different way initially. I used the 600 degrees Celsius, but technically, since we're calculating delta G naught, and it doesn't say that, there is actually does say that. We're calculating delta G naught. Oh, I didn't realize something here. Let me back up. It asks to calculate Kc, so we are using concentrations, more on that in a bit. So we calculate Kc, then we use Kc to find delta G naught, even though the reaction says 600 degrees Celsius. Since we're calculating delta G naught, we need to plug in for T 298 Kelvin. So we get a, oops, I didn't put my negative here. So we get a value for delta G of 7.0 kilojoules per mole. Now that makes sense, given that our Kc is not super small. So we expect the magnitude of delta G to not be super big. It's definitely going to be positive, though, telling us that this reaction is not spontaneous in the forward direction. Notice what I said there. Non-spontaneous in the forward direction, but spontaneous in the reverse direction. So just be mindful of that in case that comes up. All right, take a look at 1718 at the bottom of page 690. Little different problem. It says in examples 15 through 19, or sorry, 1519 and 1520, way back from chapter 15, was determined that delta G for the reaction is positive 173.1 kilojoules per mole. Calculate Kp. So again, whatever it asks for, that's what we're finding. So we use delta G to calculate Kp the same way we use delta G to calculate Kc, or vice versa, anytime. So there's our setup. We end up with 4.4 times 10 to the negative 31st, which tells us that this reaction is non-spontaneous in the forward direction. Again, we already knew that by looking at delta G, but this confirms it. Our equilibrium constant is really, really, really small, meaning we have very few products and lots of reactants. All right, practice time. Go ahead and do number 85, 698. Pause now. So this one definitely could be a green triangle. It's a pretty tough set of problems here. First of all, letter A, negative. So take a look at what happens to K when the temperature goes up. And we didn't talk about this before with Le Chatelier, but this is important to understand. If temperature goes up, which way does the equilibrium shift? Well, in this case, the temperature going up causes K to increase. Sorry, take that back. Increase in temperature causes a K to decrease. So where's the heat term then in the equation if K goes down when temperature goes up? Well, K goes down means the top gets smaller, bottom gets bigger, less products, more reactants. That must mean that the heat term is on the right side of the equation, telling us that this reaction is exothermic, and therefore delta H is negative. So the equation there for letter B is half of our original equation. So we're going to take the Kc at that temperature and square roots. So we get 4.0 times 10 to the second. That's the square root of 1.6 times 10 to the fifth. And then letter C. So I set this up in an ice table. I just put 1. It could be 100 for 100% because we're trying to find ultimately the percent, but 1 gives us a little bit easier numbers to work with. So I have my equilibrium concentrations. Notice what I did here. So 6.25 times 10 to the negative 6 is the inverse of 1.6 times 10 to the fifth. So this is the reverse of the reaction that we're given. And so I flipped the Kc. Notice that Kc is really small. So what does that mean? If Kc is really small, that means the amount of the HBr that reacts is very small. So this 2x is a really small number. Well, what is 1 minus a really small number? Well, it's going to be pretty close to 1. So what I did here is I assumed that x is small. And by assuming x is small, that greatly simplifies my setup. So I get x squared over 1 squared, just 1, is equal to Kc. Solve for x, we get 0.0025. Again, this is not a percent. Plug that in here. So we need 2 times because it wants to know how much decomposed, how much reacted. 2 times that is 0.0050. Change that to a percent, so multiply by 100, we get 0.50% of the HBr reacts. All right, next up 1719. Again, pretty similar, it's just a plug and play calculation here. You are given the Kp for a reaction, asked to calculate delta G. So just plug it in. Notice that Kp is big, means products are favored. So make a prediction about delta G. We plug that in, we get delta G negative 101 kilojoules per mole, telling us that that reaction is spontaneous. All right, number 89, give that one a try. All right, so once again, kind of similar to our last problem, increasing the temperature is going to decrease the amount of dissolved oxygen, going to decrease the amount of aqueous oxygen. That means our heat term is on the right side of the equation, telling us the reaction is exothermic. So delta H is negative. All right, so last thing, Le Chatelier's principle in industrial processes. This first one is very important. The Haber process, which involves the formation of ammonia gas. Ammonia is used in the manufacture of fertilizers. And so obviously we have lots of farming going on in the United States and we need lots of fertilizer. And so this is a very, very, very useful reaction. So let's take a look at the equation for the reaction. So you have nitrogen and hydrogen gases that produce ammonia. I guess we'll put the balance equation here. And we'll put our heat term. So there's our, oops, I didn't balance it, but let's do that. There we go. So everything here is the gas. What about the iron? Put Fe over the arrows. What does that mean? This reaction is catalyzed by the heterogeneous catalyst iron. All right, so if it is your job to maximize the yield of ammonia, what are the experimental conditions that will result in the greatest production of ammonia? So we're going to use Le Chatelier's principle. So it says in number 2, products are favored at lower temperature, right? It's an exothermic process. So if we decrease the temperature, equilibrium shifts to the right, and higher pressure. So if you increase the pressure at which this reaction is occurring, again, equilibrium is going to shift to the right, resulting in the formation of more ammonia. Here's the problem. It takes a lot of energy to increase the pressure inside of a container, and that costs money. Also, we have something else to consider. The reaction occurs, or you're going to maximize the yield of ammonia at low temperature. However, if this reaction is occurring at low temperature, what effect does that have on the reaction kinetics? This reaction, though will be products favored at a lower temperature, is going to occur really slow. So we have to have some sort of balance between kinetics and our production of ammonia here. So it says the reaction is actually carried out at moderate temperatures, so you can kind of maximize the yield of ammonia. Otherwise, it would be too slow to produce adequate yields. So I've seen this on multiple tests. Why is this reaction not carried out at really low temperatures? Well, at really low temperatures, though the yield of ammonia is maximized, the reaction is just going to be really slow. So you're going to make a lot of ammonia just really slowly. All right, the other common one, contact process, involves the formation of sulfur trioxide gas. So let's write the balance equation for that reaction. You got sulfur dioxide gas and oxygen gas produce sulfur trioxide. This one has a vanadium oxide catalyst, V2O5. Like the Haber process, the contact process is exothermic. So yeah, you're going to yield more SO3 at a lower temperature, but the reaction is going to occur slowly. So again, moderate temperature, so we can shift that equilibrium to the right, but still allowing the rates of that reaction to be fairly high. Alrighty, that concludes this lesson. Thank you for watching.